All right. This is great. Staying on. No smells or anything funky. But what I wanted to do is to see what the voltage drop was across between the batteries to here and then here, just to give a visual indication of, well, we're not going to test both scenarios with the higher gauge and therefore thinner wire. But I'm just curious what the voltage drop across this lengthier run is about. I think it's about 6 feet that I ran it. Because it has to go around, it has to go across the ceiling a little bit and then down the wall to a height. I mean, I'm over 6 foot, so it doesn't have to come on the wall that much, but just enough to be able to make it reasonably accessible. So let's reel in the lead. Reel that in. Get it over there. Cool. DC. But okay, here we go. Let's look at the batteries real quick. This is positive and this is negative. Volts. So 4.04, nice. What does that come to about? Help calculator. 1.33 volts a cell? Yeah, about 1.33 volts a cell. Right? 4 divided by 3. Yes. 1.33 volts per cell. And we could even check that too. Let's see. Let's see if they're all even with each other. 1.35. These usually are generally right on and pretty evenly matched. 1.34 and 1.36, so like within 0.02 volts of each other. Cool. So coming out of here, so we were at, what is it? 4 volts, right? Is that what it was? 4 volts? Oops, that's the wrong way. 4 volts. 4.02 volts. So let's put 4.02 in the calculator there, just so we remember it. And actually what we can do is this, even cooler. So come out of the battery. It's a pretty decent gauge wire. I think this is like 24 or 26 coming out of here, so it's decent. So 397. So it's a bit of a drop coming across the switch and out, but that's 50 millivolts. 50 millivolts. So we can actually calculate out what that drop is, but let's look at the whole thing. So now we're going to go from there to the battery plus, battery minus. $388. So 4.02 minus 3.88 is 0.14 volts. So it was a 0.14 volt drop across here. And so we know V equals IR, the voltage we know, and the current is, I know this because I measured it before, so we're going to take my word for it, but it is about half an amp. So this is pulling about a half an amp when it's running. So we're going to divide that, because we want to get the resistance, by 0.5. So about 0.28 ohms across this. That's not bad. That's not bad. And we can verify that further by turning off this, because you can't measure impedance while the thing's turned on. And we'll go into impedance, and we're going to go to the positive terminal, and we're going to go to battery plus. And actually what we're probably going to see is half of that, because it's a combination of the supply and the return. Battery plus. Oh, am I on? The wrong tab. Oh, the switch is off. Oh. Ha. Well, it's great that it's showing overload. Because the switch is off. Actually, we can measure impedance on the same side of the circuit. So I'm on positive and I'm on positive. Because it isn't shorting anything. It's not shorting anything out. But what I can do is this. This is how I'm going to have to do it. Let's just take one battery out. Just need to remove one battery. Open the circuit, turn the switch back on. Now I've got an electrical connection from the positive here to the positive here. Auto ranging point, so 0.05. And then on the negative terminal, about 0.05, so about 1 ohm. It actually may be, yeah, it may actually be about 1 ohm because the current that I measured at was when the voltage, the current I measured at was when the voltage was quite low. So that is the voltage on the battery pack, the single cell pack. So let's do a little test just to find a little fun thing here. I'm going to pop this battery in and kind of push it like that. Switch over to current, amps DC, and then that's turned on already. What I'm going to do is put one of the probes. That may not actually be the right way to do this. Maybe this way. Actually, let's do it from the positive terminal of the other battery, because the spring terminals are going to be difficult to get anything off of. So, like I said, this is a bit of a tight fit for these this enclosures. The batteries don't particularly want to. There we go. So what I can do is just put one of the terminals on the battery and then one on there. Okay, so with a more fully charged battery, it's actually 0.444 amps. It's not 0.5 like I thought it was. So the power dissipation is, let's just do relative so we can remember what this was, because I'll forget. I don't think I'm on the spring terminal anymore. That's not what I meant to do, but 0.444, I remember that. So 0.444 times 4.02. It's about 1.78 watts when it's on. That's a pretty hefty amount of power. So this thing were to run continuously, we're about 9 watt hours divided by 1.78. You get about 5 hours of runtime with this thing on continuously, but it's not going to be running continuously because it's in a closet, only coming on when you open the door. So the actual measured impedance, or I'm sorry, the calculated impedance, we measured it at about 1 ohm, half an ohm on one side, 0.6 on the other, about 1.1 to 1 ohm. So that, let's see if our calculation is close. 4.02 volts divided by 0.44. Whoops, not, yeah, 4.02 divided by 0.44. .1. Why is the impedance higher? 4.02 volts. V equals, Oh. We're looking at the voltage drop. Voltage drop. My mistake. So we were, whoop, that was a dead short. Let's kill the batteries. Let's just kill them. Hope I didn't pop that fuse. I don't think it was long enough. I think I would have heard it. I'm going to check it. Watch mistakes in real time. Okay. Let's check to make sure the fuse actually is still good. Did I pop the fuse? Oh, wait. Helps when it's in the right. Yeah, I didn't blow it. I don't think these things are capable of maybe about 10 amps short circuit. Why is it not staying on? It's kind of weird. We're having problems getting the probe on there? What's going on? What's going on? There we go. Nope, didn't blow the fuse. Cool. That's reassuring. Okay. Voltage. Last check. Positive to negative. AC. Why it does that? We should remember. 398. And then 398 to 385. So 398, 3.85, 0.13 volts dropped at 0.44. So it's saying about 0.29 ohms. Proving that there's not much of a voltage drop. So this is a pretty efficient setup. And we're only really dissipating maybe, what is that? 0.29 ohms. It's over here. Last little bit. 394. .382, 394 minus 382, 394. So, in DC, wattage equals V times I. So we got the voltage drop times the current, which is about 5 milliwatts, 0.52 milliwatts. Times 100. $52 milliwatts. Is that right? Yeah, 52 milliwatts. That's not bad. Especially when you think you're delivering 1.5 watts to the load. So this setup times 100 is roughly 96.5% efficient from the batteries to this. Now the drive circuitry and all that, but like 3.5% is being lost across the wire. That's not bad. Anyways, that's it. Testing is done. Everything functions. Good stuff. Now, I'm going to finish wiring up, wiring up. It's been constant wiring up of things. I'm going to just put some electrical tape around each of these so they don't short to each other. And less is more a lot of times with electrical tape. So you put a whole bunch or keep wrapping it around and around and around. It just makes it a lot of more of a mess. Especially when you're wrapping a wire. Could do heat shrink. I honestly don't have any heat shrink on me right now. So the electrical tape will do a good enough job. And then I will tape these two together so that it's another layer of protection. So, got those two together. Actually, they're not really. Just a slight length difference. But I'll wrap this. Let me just get 2 more pieces of tape. Oh yeah, I just remembered that I forgot to say that I did cut them purposely. When I cut this, I cut them at different lengths so that they were not next to each other. So if they did come apart, they wouldn't bridge and short with each other. It does make a little bit of a mess here with this, but we'll figure that out when I get that installed. So the last piece is the command strip for the battery pack, which is, I'm going to trim it just a little bit because I don't want the whole thing don't need the whole thing. So trim it down to size, keep a little tab below there so we can pull it off when we move. And we're set to go. This will be on all the time. The only time it won't be on is when the batteries are pulled out, so I don't really need to have access to the switch. Which makes me think that I might need to have a second one of these because the switch has a higher profile than the tape. Actually, what I might do instead, since it's still kind of malleable, is mount it the other way. So mount it this way. So I can put the tape on it. This slides down so it's holding the battery all the time. Oh, I like that. And then all I've got to do is lift up and pull away, and I've got access to the batteries. I think I like that idea. So let that sit there for a little while to might just put a second one on there just to be safe. Don't want the battery pack. The battery pack is the heaviest thing right now. This doesn't weigh anything. So I might put a second one. Just to cool. Well, that about wraps it up. I'm gonna let this cure these things need to cure for a little while before I go and stick them on the ceiling. And then that wraps it up here. And I think I'll do a follow-up video where I actually have everything installed. And we'll show how it all looks. So yeah, here's the salvaging of the of this light after many challenges that I faced getting it to be something that would be able to contain 3 of those lithium cells, and instead decided to convert it into basically one that runs off nickel metal hydride batteries like I was doing for these. But honestly, I'm going to get the same capacity, if not a little more, out of the lithium or out of the nickel metal hydride batteries as if I were to stick 3 lithium batteries in there. And I would almost argue that these are a better value, because while they may not have, they're larger, you get 500 charge cycles out of this to about 80% capacity, whereas any one of these lithium cells, if you're charging it all the way up to 4.2 volts, you're probably going to get about 300 charge cycles. So, but we'll see how in the long run that actually works out. But for now, thanks so much for watching this incredibly long electronic odyssey while I get things figured out and learn things and ended up coming up with something that looks kind of hacky, but actually I think in the end will work quite well for a remote location that is hidden away in a closet, and all you're going to see is the light coming down from it and perhaps a little battery box hanging out in the corner that may need to be changed every 2 months or charged every 2 months. Thanks so much for watching. If you like what you saw, please give it a thumbs up and subscribe. It really helps as I try to keep growing this channel. All right, I'll see you in the next one.